Okay, so we will complete 8 and 9. Asha already did a lot of explanation for the week solution of week 8 also, and I think this particular few things now we will also help you to understand. So I hope this works, and this will cover all the essential part. So let's start with a couple of examples, and I think probably I will just wait for your reaction, and if not, I will just give you a quick answer. We have already done these things, but we are just, as we discussed, that we will move back and forth and try to cover again different concepts as we are coming close to the end semester exam, and we'll do more revisions as promised. So I think that's what we're doing. So first example is two radio antennas located along the Earth's equator are separated by separated by 30 meters. The baseline is 30 meters, and the lambda is given as 6 centimeters, and hour angle, the H0, is given as 1 hour. Okay. So what is the time delay of a wavefront's arrival at the more distance antenna relative to the closer antenna? Now we know that time delay between two antenna is given by what? B of sine theta over C. Correct? We just we had this discussion earlier. So that's the thing. So you have B sine theta over C. If you just put in the angles, you will get here. All right. So you get the time as seconds. The catch is our angle is 1 hour. Yeah. So the source is then 50 degree. So our angle is equal to 0 when the source transits, right, from the zenith. And it is 15 degree. So when our angle is 1 hour, that it corresponds to 15 degree. Why? Because 24 hours covers 360 degrees. So if you do that, you'll find 1 hour equal to 15 degrees. Okay, so you can compute the corresponding time delay. What was the second question? The second question was that what is the phase difference between the parts of the same wavefront? So you have a time delay, you convert it to a phase, and that is easy. So this is what it's given. Okay. Again, look into the thing. When is this second 8-week assignment due? Anyway. So the tau is equal to B sine of theta over C, and 2 delta phi is 2 pi nu tau. So you can calculate that. This comes out to be 258.82 pi radian. Okay. So remember that it takes so full phase. If you have cosine of n pi, again repeats the function, right? N is an integer, so it has a time period repeats. So here we have 0.82 pi as additional. So that's the phase difference we have completed. Okay, this 258 pi is same. Okay, so 0.82 pi radians is the difference. Any issue with this? Hearing none, we go to the next one. Example 2, imagine the source in the previous example located at an hour angle of +1 hour or 15 degrees to the west. 15 degrees to the west of the baseline's zenith is a point source with a flux density of 3 Jansky. So based on the expression, we can use this. This R is equal to F nu cosine of 2 pi B over lambda sine of omega ET. What calibrated value is measured by the 2 antennas acting as a multiplicative interferometer. Then according to the same equation, what are the amplitudes and phase of the detected fringe? Okay. So this is the correlation coming out from the interferometer, multiplying interferometer. So we have determined the fringe phase to be 0.82 radians from the previous example. So the response of the interferometer is 3 cosine of 0.82 pi radians, or so then the Jansky value comes down because you have a fringe function. So that's how it looks like. As a single measured value, this should be strange. The information we can get from this interferometer does not come with a single measurement. We need to measure the output for a range of times to detect the oscillations of the fringes. Although we could not infer the answer to this question from this single measurement, from setup of the earlier example and our calculation in the previous example 1, the part 1 of this example, we know that the amplitude is 3 Jansky, which is already given, and this is 0.8 radians. So that is, we can then calculate what is the instantaneous value of the flux. Now, example number 3, the multiplicative interferometric observation in example 2. How long must we wait to measure one full oscillation of the fringes? Again, it is the same thing. It talks about the fringe spacing. So you have a sinusoidal function. So any integer multiple of pi, it will come to the full period. And so you can calculate from there. So you can go through this as well. Example number 4, radio galaxy Cygnus A contains 2 especially bright points of radio emission separated by about 0.71 arc minute. Imagine you set out to build your own interferometer at a wavelength of 6 centimeters and decide to use the bright galaxy to test it out. Over what range of baselines should you make observations of Cygnus A to be able to measure the angular separation between these points? So very clearly, you have 2 hotspots of the Cygnus, and they are separated by an angular separation of 0.71 arc minute. And the wavelength is given, that is 6 centimeters. So what do you have? You have a baseline, right? So you have a resolution theta is given by lambda over B max. So you know lambda is 6 centimeter. You know the theta, which is 0.71. So you have to have baselines which, so your baseline has to be higher, larger than the value corresponding to this. So you put in all the values, you convert 0.71 arc minute radian, you get this particular value, 2 to the power minus 4. So you put that, then baseline comes up to 290 meters. So in order to resolve the source, you need to have a baseline length greater than 90 meters. So this ideally should be, B should be greater than or equal to 290 meters. Because if it is less than 290 meters, then we will not be able to do it. feel free to ask question if you have any. Example 5, in an observation of a pair of point sources using an array of antennas, the visibility amplitudes are seen to oscillate with a spacing period equal to that of the expected. That is equal to 1 over the believed separation angle of the other sources. However, the amplitude never goes to 0, oscillating between 2 and 4 Jansky. Why? What does it mean in terms of the sources? So you can use visibility function VAB as FA square plus FB square. You have two sources, and you can kind of derive the expression like this. So maximum occurs when the cosine part will be maximum equals to 1. So 4 Jansky is equal to this, and that is FA plus FB, which is simple. And the most minimum occurs when it is negative. So it goes from, when you have two sources, it goes from FA plus 1, FA plus FB to FA minus FB. So if you have two equations, you have two unknowns, so you can solve for the individual flux density of the sources. Next example, with an astronomical reception system, diverse elements collectively influence the comprehensive noise temperature. This system encompasses an antenna characterized by a noise temperature of 80 Kelvin. So T N of antenna is equal to 80 Kelvin. It operates in an environment with a physical temperature. Ambient temperature is given by 500 Kelvin. Demonstrates the efficiency. So eta is 91%. Additionally, there exists a transmission line functioning at 400 Kelvin, boasting an efficiency. So a transmission line is at 400 Kelvin and an efficiency of 90%. Okay. The receiver, on the other hand, comprises of initial 3 stages, each marked by a noise temperature of. So initially 3 stages. So receiver for first one is of 100 Kelvin, and gain is 20 dB. The central query pertains to the calculation of full system temperature within this particular configuration. Okay, let's see how to go about it. So there is an antenna which is having a noise temperature of 80 Kelvin. Ambient temperature is 500 Kelvin. Efficiency is 91%. It is connected to the receiver via a transmission line. So an antenna, then connected by a wire or transmission line to a receiver. So the transmission line characteristics given by its ambient temperature is 400 Kelvin and efficiency is 90%. So let us see what are we going to derive. So yeah. So total receiver noise temperature, which has 3 different stages. Each one of them, yes, that was a misreading. So receiver, on the other hand, comprises of initial 3 stages, each marked by a noise temperature of this. So this is true for 1, 2, 3, and gain also is true for 1, 2, and 3. So then we have done this problem before, that you have the how to write it? TR is nothing but TR1 plus TR of 2 multiplied by the gain of 1, then TR of 3 divided by gain of 1 multiplied by gain of 2. Okay, so that's where you finally come out for the total receiver noise temperature given by 101.01 Kelvin. And system temperature, then if you put it about there by all the efficiency parameters, it finally comes out to be 274.96 Kelvin. Okay. Questions here? Let's move on. So in a particular, next example, in a particular observation, we have Umax minus Vmax. Am I audible? Paul? Asha? GB Raghav Krishna?
Yes, sir.
Yeah, great. Thanks. Thanks. So in a particular observation, we have Umax and Vmax is given by 50. Always happens. Yeah. So Umax and Vmax is given by 50 kilo lambda. So they are corresponding to the Pmax, right? That goes to Umax. That is given by 50 kilo lambda. So it in terms of the lambda 10 to the power 3 lambda. Okay, so what is the lambda value? So FWHM is 9 arc minute. So the FOV is half power beamwidth is 9 arc minute. And if we desire to just meet the Nyquist sampling rate with no oversampling and to image the full primary beam of the antennas, what should be the pixel and the map sizes be? Okay. Yeah, so essentially we just discussed this in a bit. So you have when we do the imaging, we have the UV. Okay, so we have the visibility in UV grid. Okay, since the maximum baseline is already given, so that's the extent of the UV values. Okay, so for each pixel, you kind of consider that to be of 1 over twice of this UV values, because that's the inverse in the theta. So you're looking towards in the theta domain. So that is kind of proportional to the inverse of the U max, right? Because U and theta are the Fourier conjugate. Remember, V, which is defined by UV coordinates, is nothing but a Fourier transform of I, which is in the theta, x, theta, y, you can say, or LM, whatever you want to write in angular coordinates, assuming that the A is equal to 1. It's a special case. Okay. So A is equal to 1, but A has a finite size given by the half power beamwidth. So we will only consider that portion of the sky which is coming from within this 9 arc minute section of the sky around that point in center. So, okay, let's go back to further. So Umax, we know that is given by 50 kilo lambda, right? Now lambda is, has it been defined? Yeah, so 50 kilo lambda, so 50,000, and twice of that because you are doing a Nyquist. So twice of that, that is given by 2 arc seconds. So delta x or delta y or theta is given by 2 arc seconds. Now to image the primary beam, you have a primary beam size of 9 arc minute or 9 times 60 arc seconds. So with each of the cells given by 2 arc seconds, you have to simply divide this by 2 arc second. So you have a 9 times 30, that is equal to 270 pixels. Okay. So what happens is that, let me just a little bit take one more slide to explain this particular phenomenon. This may be very bit. Yeah, so we can just go ahead. So yeah, so we stopped in that thing discussing that VUV is nothing but a Fourier transform of ALM times ILM. Okay. Now, if I just take it out, assuming this is equal to 1, however, we only concentrate on that part of the sky which is within the half power beamwidth. Okay, but within half power beamwidth also we assume that the response of the primary beam to be equal to 1 or flat. Just a simplification example, simplifying assumption. Sorry, just to make life easier. So you have to only image the part of the sky which falls within the half power beamwidth, and that's it. You're going to do more than that. Given that, you have now only VUV, which is a Fourier transform, two-dimensional Fourier transform of sky ILM. Very simplistic assumptions. Now, for a Fourier transform to take place, you know there is something called a fast Fourier transform, which is only applicable if you can grid this data. So what you do is simply you grid the data in a regular Cartesian grid. So you have different values for the grid. So certainly it starts from the center, which is U equal to 0 and V equal to 0, and it extends to the maximum value of U max and V max. Okay, and that is given very clearly from the maximum baseline of the interferometer. There is no doubt about that. That part is very clear. Now, given that, we just take a Fourier transform of that to give to the sky plane, giving the ILM. So, because it's the fast Fourier transform, so total number of elements. So, suppose this is NU times NV, number of grid points. That will also be equal to NL times NM. So this thing will be equal to that. So NU times NV will be equal to NL times NM. In fact, these values in both axes should be equal. Equal is a square grid in some sense. So the maximum baseline corresponds to what? The minimum in the angular separation, right? That's resolution, right? So there's an inverse. So theta or LM is proportional to 1 over U. Okay. So the maximum of U max is corresponding to the minimum value of the theta. Okay. So what did we did? We had the U max. We calculated the theta mean, the resolution. This is the resolution. We considered the Nyquist sampling, so we made it twice of that. And then with that, we know what is the extent of the beam is. So that was equal to 9 arc minute. And theta mean was equal to 2 arc seconds. So we calculated total number of theta. We needed is 270 pixels to image this. Okay. That's the easiest way to understand this one. Questions? We are running very close to the time. We wanted to finish by 8. Just give me another 5 minutes. We will wrap it up. So next example, we have imagined that we wish to use an array with baselines from 10 meter to 30 meter to explore an area of the sky for new sources. If we want to be able to detect sources within a field of view of 10 arc-minute on a site, what constraint does this pose on the bandwidth of the observation? I would say watch the detailed video, which will be coming up tomorrow for this. You can get anything. This will also be uploaded there. Example 9, we want to detect an unresolved source observing at 22.2 gigahertz. A previous 22 gigahertz survey with a sensitivity of 0.3 Jansky did not detect this source. We will use an array of 3 antennas, all with system temperature of 50 Kelvin, effective apertures of 30.4 meters square, observing a single polarization with a bandwidth of 50 megahertz, assuming correlation efficiency of 0.8. If we fail to detect the source, we would at least like to halve the upper limit on its flux density, using 5 times the RMS noise as a conservative upper limit or a non-detection. What is the minimum amount of time that we should observe the source? That's question number 1. Question number 2 says, what is the minimum flux density that will be detected in the cross correlations for an integration time of 2 minutes? So this deals with something called sensitivity. We discussed a part of it. We didn't go deeper. So sensitivity for an interferometer is given by this, where your system temperature is same as your single dish system temperature. But instead of now, for single dish, we had only T6 over delta nu times delta T. That was given a sensitivity limit. Here we have, for interferometry, we have more number of samples. So that's multiplied by n into n minus 1, which gives you the effect of the total number of baselines. Okay, and there will be some constants, which is given by C. Okay. So if you insert all the values, so you basically have 0.03 Jansky per synthesized beam to match the minimum SNR. If you put on top of that, then you finally get it to observe the particular source for delta T equal to 119 seconds. Don't worry too much about all these things. So there to make the thing complete. This won't be, this a bit more complex, and we will not make it as a part of the assignments or the final exams. Even if we do, it will be very simple. Don't worry if you don't understand too much. We will try to explain it more in even this week's lecture, as it will be available soon. Okay, so yeah, so the minimum flux density, if you go by this manner, detectable is 0.0518 Jansky. Example 10, we obtain visibility data for a particular astronomical object. A 3D plot of the visibility amplitude is shown in figure A. The amplitudes are shown in the grayscale. U is plotted on the horizontal scale, etc. So this is the visibility data in the figure A is shown here. And figure B shows the amplitude versus the UV distance. What can be inferred about from this particular source? Now you have seen a lot of this 2D Fourier transform pairs, right? So by looking at this particular plot, what can you make up? That's all we're asking. The source is separated by 6.3 arc minute. Sources are, it looks like a pair of sources. The visibility amplitude oscillates with a period of 550 inverse radian. This must compare to a pair of sources separated by 1/550 radian. With a peak amplitude of 6 Jansky and minimum amplitude about to be 0, then this gives you the minimum separation of 6.3 arc minute, and two sources of similar, exactly same flux density of 3 Jansky, because it 3 plus 3, we're at the peak. We have seen that example, FA plus FB, when the cosine function peaks, and when it goes to negative, it is FA minus FB. So in this particular case, it is 3 plus 3 to 3 minus 3. That matches, so it is 0 in the minimum and 6 Jansky at the maximum. So that's the two sources, equal surface brightness of 3 Jansky, separated by a 6.3 arc minute. So you can infer a lot from just the visibility plots. That's what I'm saying. Let's look at this 11th example. I think we're coming close. Yeah, so at another visibility plot, a second astronomical object is observed. Its 3D visibility plot shows an amplitude decreasing with UV distance in all directions. A 2D plot of the amplitude versus UV distance, which is given by this one. It shows about the structure. So it's like an extended source, Gaussian source kind of, which has a, the source size is roughly a Gaussian width of WHM of 1/450. And so that gives rise to 7.6 arc minute. How do we get this 450? It's kind of from where it goes to, from 8-ish to about 4. So it's kind of there, the middle of 300 and 600. So that is 450. So it goes from its peak value of 8 to its half power value of 4. So that's how it is calculated. So FWHM is about 1/this, so you get about 7.6 arc minute. Okay, and the peak flux is about 8 Jansky. There are two, the visibility function for various brightness distribution models. Solid lines, amplitude, and dashed lines are the phases. This is what which is given, and you can take a look. So we have done it also. So Gaussian, displaced Gaussian shape extended. So you can just look at the individual Fourier pairs. It's very self-explanatory. If you look at it, you will understand. We have done it in the previous discussion as well. You just go through it, and when it's available on the portal. Example 13, we learn a new source reported to have an angular size of approximately 3 arc minute with a brighter central core component of about 5 arc seconds. To obtain a reasonable map of this source at 1.35 centimeter wavelength, what baseline length should we use? So again, the same thing, similar expression. So the baselines correspond to about 5/3 of an arc second. The angular size of the source is given by this radian, and the core is approximately 8.07 × 10⁻⁷. So that's how it needs to resolve the particular source. So the UV distance is then at the order of this. That corresponds to 15 meter of length, at the observing frequency or wavelength of 1.35 centimeters. And approximately 1700 meters or 16.70 meter to resolve the core. This is for resolving the core. So 15 meter for resolving the brighter central core component of about 5 arc seconds, and 3 arc minute is basically the angle size. So as the core is much smaller and compact, you need a longer baseline to resolve that. That's about at 1.35 centimeter, it's about 1670 meters or 1.67 kilometer is the baseline, and 15 meter is for the just resolving the source. Okay, thank you. That's kind of brings close to what we want to discuss and share with you. So I can stop here and